Hello again, and this is a video that's going to look at different types of numbers. So this is again part of the number section of what you're going to need for your test. So here we go. Whole bunch of kind of definitions coming at you, unfortunately, so just bear with me, but it is important stuff that you need to be able to know and recognize. Right, here we go, square numbers. So I do pretty much what they say on the tin. It's numbers that can be arranged in a square pattern. Now that's the first one, and I know that doesn't much look like a square pattern, but bear with me and you'll see why that is actually a square number. So that's the first square number, which is 1. The next one, there you go, that's looking much more square shapes. So that's 4. So we've got 4 dots there arranged as a square. The next one is 9, it's a 3 by 3 square, and then 16, and so on. So the first one, that is actually a 1 by 1, 2 by 2, 3 by 3, 4 by 4, and so on and so on. So what we get with the square numbers is they're made from just timesing a number by itself. So all the square numbers are there. So we've got 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, and so on, all the way up to 10 times 10. And you do need to be able to recognize those, because you might be asked in the exam to kind of pick out which ones from a whole bunch of different numbers, which ones are the square numbers. So they're the ones that are made just by timesing a number by itself. Interesting thing about the square numbers is that if you look at the difference each time, what we're doing essentially is kind of adding on 3 to begin with, then add on 5, add on 7. So the difference between those numbers just increases by 2 each time, and those are the odd numbers. You're probably not going to get asked about that, but it's just something that I think you may or may not find interesting to do with the square numbers. Right, that's the squares. On we go. Next thing we're going to look at are the cubes. And the cubes work in a very similar way, except that these times they can be arranged in a cube pattern. So there's my first cube number, which is just 1, for the same reasons as 1 was a square number. The next cube number is that one, so you can see I've got, if you count the squares, I've got 1, 2, 3, 4 on the top, and I've got 1, 2, 3, and the 1 round the back that you can't see, 4 on the bottom layer, so that gives me 8. So that's a 2 by 2 by 2 cube. And yes, you guessed it, here's the next one, 3 by 3. So again, if you have a look at the top layer here, I've got 9. The second layer will have 9. The third layer will have 9. So I've got 9 plus 9 plus 9. That's 27. And that one is 3 by 3 by 3. And then there's our 4 by 4 by 4, which is 64. So we've got 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3, 4 times 4 times 4. And so you can see they're built in a very similar way to the square numbers, but instead of the number just being times by itself, it's times by itself, and then times by itself again. And there are our first 10 cube numbers, 1, 8, 27, 64, there's 5 times 5 times 5. By the time we get up this end here, that's 9 times 9 times 9, 10 times 10 times 10 is 1,000. Now, those ones are a bit more difficult to remember, but you would be expected to kind of recognise at least, I think, probably about the first 5 of those, and maybe 1,000 as well, but don't worry massively about the bigger ones up here. But these first ones, definitely, I think you should know those ones. Right, and then the third set of numbers are the triangular numbers. So, again, similar kind of deal, we can arrange them in a particular pattern, and this time we're going for a triangular pattern. There's 1 again, so 1 is a cube, a square, and a triangular number. And there's my triangular pattern for the next one. So I'll just put on an almost like an extra row on my triangle here. So I've added on 2 there. And then my next triangle, there's the original triangle with 3, and I've just added on a row of 3. And yes, you've guessed it, the next one we're going to be adding on a row of 4. There they are. And essentially what you do is just keep adding on extra rows of increasing number of dots. So we've got 1, 3, 6, 10. The next one will be 15, and so on. So that's 1. That's 1 plus 2, because we've got 1 plus 2. Here we've got 1 plus 2 plus 3. So we've got that. Here we've got 1 plus 2 plus 3 plus 4. There we go. And that's why I said the next one will be 15. So 1 plus 2 plus 3 plus 4 plus 5. And they keep going as well. And so there are your triangular numbers. Again, it is useful to be able to know where they come from, be able to recognise them, but I think the more important ones are your squares and cubes. And just to chuck a little bit of extras in here, so we've got that, we've already mentioned that before, that to get from one triangular to the next one, you're just adding on an increasing amount each time. Each of these red numbers down here is just the amount you need in the extra bottom row. But slightly more interesting is this one. So 1 plus 3 is 4, 3 plus 6 is 9, 6 plus 10 is 16, and if we keep going, all of those blue numbers look familiar to you? Hopefully they should. Yep, you guessed it, those are the square numbers. So the square numbers are made up from the triangular numbers. Okay, so those are a kind of sets of numbers you need to be able to recognise. The other ones, hopefully you're familiar with these terms, but we're going to go through and just make sure. You are kind of, a lot of students find that particularly factors and multiples tend to get mixed up a bit, so I'm going to hopefully try and straighten that one out for you. So factors of a number, those that go into another number, so they'll divide into a number with no remainder. The easiest way to look at these is just to do an example, and you'll see what I mean. So if we take the factors of 18, what I'm going to do is say, well, let's just start writing out pairs of numbers that multiply to make 18. So the first pair, the simplest one would be 1 times by what? Well, that's going to be times by 18. So 1 and 18 are a pair that multiply to make 18. Both of those will divide into 18 with nothing left over. And now we've just got to keep going through the numbers. So the next one, will 2 go in? Well, clearly, yes, it will. 2 will go in, and that's going to be paired with 9. So 2 and 9 is a pair. 3, will that go in? Well, yes, it does. And what's it going to be paired with? That's 6. The next one is 4. Will 4 go into 18? Well, if we do 4 into 18, we'll have some left over, so that's not going to be a factor. 5, no, that's not going to go into 18. And by the time we get to 6, we'll notice we've already kind of got to the middle here, with 6 is already on our list, so we don't need to go any further. So we've now got our complete list. 1, 2, 3, 6, 9, 18. Those are all the numbers that divide into 18 with no remainder. Right, prime numbers. Now the reason I did primes after the factors is because we need to know about factors to be able to know about primes. And the technical definition of a prime number is that it's got, exactly 2 factors. And those factors are always going to be 1 and itself. So for example, if I take 19, what numbers can divide into 19 with nothing left over? Well, it's going to be 1 and 19. 2 won't go, 3 won't go, 4, 5, 6. None of these numbers will divide into 19. And we find that those are the only 2 numbers that go into 19. Now, this one's an important one. 1 itself is not a prime number. And the reason is, comes back to our definition above here. Our definition said it's got to have 2 factors. But when you think about it, 1 has only got 1 factor. 1 is the only number that goes into it. So 1 kind of loses out. It's not a prime number. It loses out on a bit of a technicality. So there's our list of prime numbers, 2, 3, 5, 7, 11, 13, 17, and so on. And again, you'd be expected to be familiar with some of the ones lower down, probably up to maybe about 31. Not so much these ones up here, but definitely kind of the smaller prime numbers you would expect to be able to recognise those ones. Okay, so that's the primes. Moving on again. Last set we're going to look at here are multiples. And the multiples of a number are those that are on its times tables. So, for example, for the previous slide we did factors of 18. Now let's do the multiples of 18, for which we're going to need the 18 times table. So we've got 18, 2 18s are 36, 3 18s are 54, 72, 90, 108, and so on. I've put the dots here because that number list is going to go on and on and on forever, and that's what kind of the hint there is saying. It's like, if I wanted to write out the factors of 18, I can write out a complete list and know I've written them all. However, there's no way I'm ever going to be able to write down a full list of all the multiples, because the multiples, let's say, like the times tables, go on forever. So if you want a way to remember the difference between factors and multiples, factors, you can write them all down. Multiples, you absolutely can't. So if you're asked to write a list of multiples, you'd only be asked for maybe the first, maybe 4 or 5. Okay. And then finally we're going to finish off with these terms HCF, LCM and prime factors. HCF, highest common factor. And the highest common factor of 2 numbers is the highest number that is a factor of both. And again, let's have a look at an example, because then it's going to make a lot more sense. So we want the highest common factor of 24 and 36. So first thing to do is to write out our lists of factors of those 2 numbers. And then we can start looking at the 2 lists and doing a bit of comparing. So here we go, factors of 24. We've got 1 and 24, there's a pair. 2 and 12, 3 and 8, 4 and 6. 5 won't go, and then when we get to 6, we've already got 6 here, so we know we've got to the middle. So there's our complete list. Likewise, let's do that for 36 as well. So we've got 1, 36, 2 and 18, 3, 12, 4, that'll go in, 9, 5, that one won't go, 6, and 6 only won't because 6 times 6 makes 36. So that's kind of sitting there on its own in the middle. And again, I've reached the middle, so I know I've got them all. Now what I need to do is start looking for numbers that are on both lists, and I particularly want to find the highest number that is on both lists. So if we look for common factors to begin with, 1 is certainly a common factor, 2 is there, 3, 4, 6. All of these are common factors, but as you can see, our highest common factor is 12 because it's the biggest number that appears on both lists. Lowest common multiple, as you might expect, it's now the smallest number that is a multiple of both. So basically we're looking for the smallest number that is on both times tables. So let's use 24 and 36 again, and I'll do all the thinking for you and write out the times tables of 24 and 36. We're going to use exactly the same methods we did before, so here comes our list. There's our 24 times table, and I'm sure given enough thinking time you'd be able to get those numbers as well. There's our 36 times table, and so now what we're looking for is the smallest number that is on both lists. Can you spot it? There you go, there it is, 72. So 72 is the smallest number, it's on both lists, and so it is the lowest common multiple. And the last thing I want to mention in this video is prime factors. Now prime factors pretty much do what they say on the tin. They're the factors that are also prime. So for example, if we take the factors of 100 and say, okay, well here comes our factor list, 1 and 100, 2 and 50, 4 and 25, 5 and 20, and then 10. So there's our list of factors. And then what we now need to do is look for the primes. So can you spot them? Which ones on that list are the prime numbers? And hopefully you'll have spotted 2 is prime, 5 is prime, and remember we said earlier 1 not a prime number, so it's not a prime factor. The prime factors are 2. And another interesting fact about the prime numbers is that we can take any number at all whatsoever and write it as a product of its prime factors, and hopefully you're familiar with the term product. A product just means by times them together. And again, this might be something that you get asked to do on your test, so let's have a quick look. So let's take 100, and what we're going to do is I'm going to do something called a factor tree. So I'm going to split it up into its factors. So I'm looking for 2 numbers that are going to multiply to make 100. So just to keep my life simple, I'm going to pick 2 and 50. 2 times 50 makes 100. And what I've done is put a circle around the 2 because a 2 is one of my primes. So that one I'm going to stop. I don't need to split anymore. I'm now going to look at the 50 and say, okay, can we split that up a bit further? Can we find 2 numbers that multiply to make 50? Clearly we can. I'm picking 2 again, and this time with 25. And again, 2 is prime, so that one's stopping. I'm going to go over to this branch here. Numbers that multiply to make 25, well, 2 is no longer going to work because 25 is an odd number. So can I find a pair of numbers that multiply to make 25? And I think I can. I'm going to use 5 and 5. And again, I've put those in circles because again, now we've hit 2 more prime numbers. So my prime factors, we said were 2 and 5, and you can see them here in my tree. So what that means is I can take the number 100 and write it as a product, a sum that involves times. So 2 times 2 is 4, 4 times 5 is 20, 20 times 5 is 100.